Hello everyone, welcome to this tutorial. A lot of students keep asking me how to verify the performance of an operational amplifier. So I thought to upload a series of tutorials where I will try to show you how to measure different performance parameters of operational amplifier or OTA in Cadence. So to demonstrate that, here as an example, I am using a folded cascode OTA single-ended. This is implemented in GPDK 180 nanometer technology, and here I'm not going to discuss about the design, as this is from you can find this in the textbooks also, but I will focus on how to verify the OTA. Okay, so this is the schematic, and then you can see I created a symbol of the same to use it in my test bench for verifying the performance. And the first test bench or the first analysis which we are going to do, or the performance verifications analysis which we are going to use here, are DC analysis, AC analysis, and power consumption. So I'm using a capacity load here around 1 picofarad, and this is the same folded cascode OTA, input, output, and VDD, and power supply and ground. Now let's go to launch ADL. Okay, so I launched the ADL here, and first of all, let's give the inputs. What are my inputs here, and the power supply and everything. So I can go here, set up stimuli, or there's this click button here. I just click here, and I define this all these ports here. So VSS is ground. I just keep it ground. Okay, and then VP, I just give the input voltage 1 volt, and okay, my caps lock is on, and AC phase, and let's give it 0, and then VIN, same DC voltage, some AC magnitude, and to keep it differential, I'll give 180 degree here, and power supply I'm using here 1.8. So when you are designing the OPAMP, you need to depending on the technology and what are your values, you have to simply enter here and proceed with the following the same steps. So the first analysis which we are going to do is DC analysis. So for that, I'm going to go here. I'll choose analysis like from here, or simply click here. So this window will come up. So I'll select the DC here, say the DC operating points, and if you want to see the impact of, so basically DC analysis, it's almost used on every analog circuit whenever you want to design any analog circuit. So we try to determine here the operating points or the initial conditions of our transistor while you are applying a DC voltage or current. Okay, and this also you can sweep the temperature or any design variable or component parameter extra to see the impact of temperature on your operating points or your node voltages or currents, etc. But for now, let's keep it simple here. I just select this and press OK, and then I run it. Okay. So when I run it, a log file will come here, just trying to show me if there are any warnings, errors, and something stuff. So there is no error. I just okay. Now let's see how to see the operating points of our transistor. Yeah. So the first way is I go here, print. I can print the DC node voltages or DC operating points also. So for example, let's say I want to print the DC operating points of a specific transistor. Okay, so I just click here and just descend into this symbol. Okay, and so this here, now for example, I want to display the operating points of this transistor NM5, which is a PMOS. So I click on this one, so I get for the NM5 here, I get all the DC operating points. Okay, so similarly, if I want for, let's say, some other transistor also, now I can go again here, print, or you can see here there is an option here this option here, I can simply click here. It's the same from the ADL window. So I just click here DC operating points, and now I want to, for example, for this PMOS here, or let's go to the NMOS. Okay, so NM7 here. So you can see here NM7, so it will display all the parameters. So this is one way to check the DC operating points. And now the second way is that, for example, if I want here to display them, I don't want to go to that table and see there in the other window. I want to see it here every time. So I can simply go here again, and results, I'll go to annotate. So DC operating points. So I will just click on this, and you can see here I'm getting by default the DC operating points which are here 4. They are getting displayed here. So for example, depending on your design, you are or the position where you are using a specific transistor for some specific purpose, you are into some other operating points, you can display them also. So the way to display them is, you can see here there is this annotation setup form. Click on this, and a pop-up window will come up, and just select here cell for NMOS. I want to plot also. I want to see the region of operation also, because when we are designing an amplifier, we make sure that all the transistors are in region 2. So in Cadence, region 0 is cut off, region 1 is triode, region 2 is active, and region 3 is subthreshold. So now I will press OK. So you can see here I'm displaying now also the region of operation for my transistor. So I can also define R on or beta or some other parameters which I'm interested, or some capacitance also. So this is how you can display the operating points, and which helps you to when you are doing some optimization on your design by changing some node voltages or the aspect ratios. You can every time see here what is the current and what is the transconductance or the region of operation, something like this. So this is the way. One is to here go results, print or annotate, and you can also go to annotate DC node voltage. I click here, so I get all the DC node voltage also printed every time. Okay, it's from the ADL, or I can simply go here and I can simply click on this. Okay, so this is the DC analysis. And then the next is we'll do the AC analysis. Again, I go here, I choose the analysis, AC analysis. Yeah, it's used to calculate the small signal response of a circuit, usually with respect to frequency. So I keep the sweep variable here, frequency as it is, and I sweep the frequency from 10 to 10 gigahertz, something like this. And yeah, just press OK. Keep everything OK. You can also sweep type. You can make it logarithmic and points per decade 10, or you can keep it automatic also. Okay, and then I just press OK, and now I simulate it. Okay, so I simulate it and I see the simulation is over. There's no error. Now I have to, when we do the AC analysis, we are interested to know the gain of amplifier, the phase response, the phase margin, the unity gain frequency, or unity gain bandwidth, or the bandwidth, these parameters. Okay, so what I will do is, so there are again many approaches. So one is straightforward, which is I go to the results, I go to direct plot, and here, so whether I want to plot the AC magnitude, the dB10, 20 phase, AC magnitude and phase together, or AC gain and phase. So the gain is with the dB20 and AC magnitude is without. So this is the straightforward approach. So I just select here AC gain and phase. So I just click here. Then I need to define the output and input. So first I click on the output, and then the second I click on the input. So I just click. You can see the colors are also changing when I select the nets. And automatically when you click the two nets, output and input, it will plot the gain and phase response. Okay, so you can see here the first is the phase and the second is the gain. And if I click V is for vertical, I can see here my amplifier has around 72 dB gain. Yeah, and if I slide it, for example, the unity gain frequency, if I would like to find it will be around 0 dB. I am trying to go approximately, let's say 19 megahertz is something around, and my phase mask is around 88 degrees here. Okay, and let's see the bandwidth. If I want to display from here, I just click here on this gain response. I click M is for markers. So now, for example, I have here 72 dB. It's showing me here. Okay, let me do it like this. Okay, and now I want to see the bandwidth. So one simple way is to see, I will just do -3 dB here and see it here. So I just click on here, pointer marker properties. I simply press Q and make it Y mode here. And so 72 minus 3 is 69. I just press OK. So you can see here my bandwidth is around 4 kilohertz. Okay, for my amplifier. So this is one way to, you can display here. The other way is which is more efficient, and I prefer that because that's a kind of one-time solution. You can also do here, what you can do, you can simply right click here on this phase and send it to the ADE, and similarly here you can send it to the ADE, and or you can send them to the calculator, try to find the bandwidth and all those things. I'll show you also how to do that. So for example, right now I send them to the ADE. Okay, so let's go to the ADE here. We see what we have. So you can see here I sent the ADE. Now next time when I do the simulation, I don't need to go to the print and do that again, direct plot. So it will be automatically here because I defined it here. Okay, and to make it a better understanding, I just give the name, like let's say if it is phase, PHASE, something like this, and yeah, gain, I just gain something like this. Okay, and again, just going back here, you can see here the gain expression. This is exactly what we are going to do in a calculator. We are going to write the same expression in the calculator also. Okay, so this was one approach, but let's go to the other approach. I will go here, tools, calculator. Okay, and now first of all I will select the output and input for which I want to plot my AC response. So because I did the with respect to frequency of the AC analysis, so I will set VF, which stands for voltage frequency. VT is for transient and VDC is for DC. So I select here VF, I select the output, it came here, and then again off, VF input, and then I select this divide here, so V out by V in. Okay. Now the first thing is we would like to plot the gain. So that is, I will go to this function panel here. I select as 20, so dB20. So this is the expression for plotting which is the mathematical expression for plotting the gain of the amplifier. So I can also print it in a tabular form. For example, there is this option here, display the results in a table. I just click here. I can see here all the gain values for each frequency. So for example, you can see here my gain is around 72.80 dB. Okay. But the other way is I can also plot it in a wave form, like here. Just click here in the next one. So I click here, so it will plot the gain response. Okay. But instead of going to calculator every time and writing this expression, I will like to send it somehow to the ADL, save it here in the outputs, so that whenever next time I do the simulation, I can simply run and see all these values. So what I will do is, so there is option here next, send buffer expression to the AD outputs. So I click on this, it will send this expression to the outputs. Okay. Now similarly, let's go one by one, and here. Now from the gain, what I would like to know is bandwidth. Okay. So just be careful here. So the bandwidth here, it automatically, this function takes the dB20 with itself. You don't need to define that. So now I want -3 less. I want the value of the frequency where the gain is 3 dB less. So I just select it to keep it as it is 3 and press OK. You can see if I want to show it here, I just click on this. You can see here my bandwidth is around 4.4 kilohertz. And for future reuse, I will send it also to the ADE, and then slowly I will go to the other functions also. Let's now keep the expression as it is, and I try to find here unity gain frequency. You can see here, so it's around 19 megahertz. Again, I will send it to the ADL, and then similarly, now let's move to the phase. Okay, so I remember it by heart, but you can search it here also, the phase, all related to phase. Okay, so here I can plot it also. You can see here the phase response, but let me send it the ADL, then we can plot it from there also. And then let me take the phase margin also, which we are interested to know from the AC response. So I can select here, you can see the phase margin on 87.90. I send it to the ADL. Okay. Now let me close this calculator. Now I think we took, I think, all the parameters which we needed from the AC response. I just close it and I go here. You can see here I have all the expressions here, the outputs which I would like to plot. Okay, now let's make it move in a presentable way. I just double click here in one of the expressions and I give the names here. So for example, I give AC GAN for this, and then the next is bandwidth. I will keep it as it is, bandwidth, and then let's keep this UGF, and then next is AC phase. So HASE, it's an open loop also, but let's keep it phase margin. Okay, so now I have all the parameters which are which were interested in the AC analysis. Now next time when I simulate it, you can see automatically I am getting the response, AC response here, gain and phase, and also I am seeing the values here, the bandwidth, the UGF, and the phase margin. So for example, if you are interested to do the PVT simulations also, process voltage, temperature variations, and also the Monte Carlo, you can do like this and define them like this, and then you can see the impact of PVT on your band, UGF, or phase margin. I will also show this in the coming tutorials, but let's for now do step by step. So this is how you can basically plot. And now the third is to know the power consumption of my amplifier or any other circuit in general. So one thing would be simply I will see the current coming from power supply into voltage V into I, its power consumption. But the other way, which is from the tool I can do, is I just go simply here outputs, save all. So basically I select these signals, I save all here, and the power signals output and everything, both all, and I save it and I run it here. So this is the, again, because my AC was selected here, but how I can see the power consumption is I can go here browser. I think yes, Windows Assistant browser, not browser. I just click here on this one. So I see a window coming here, and I click on this DC op, double click on this. So you can see the first PWR. So this is the power consumption of my amplifier, 3.15, or let's say 31 micro. Yeah. And if I want again to save it in the ADL, what I will do is I just right click on it and I will, I think, send it to calculator. Let's see, I hope it works. And then from calculator I send it to the ADL. I will give it a try. I hope it works like that also. Yeah, okay, so you can see here I could say the power also. Okay, so yeah, this is DC power, so I can write it power consumption. Okay, so power consumption. Okay, so yeah, so here I have all the parameters here. Now I can simply run it every time, and it will give me the AC response also plot and the numbers here also. So now what I will do is I will save this for my future use. I don't want to again write these expressions or something, create again this environment. So I just save it here in the cell view with this test bench DCAC which I have created. I will save this state here. I can give also some name here also, but I will keep it as it for now, and then press OK. So yeah, now for example, if I close it and I in future want to again do some simulation, I just go to ADL and load the state here, or you can go here also. I think yes, session load state, cell view, it's here, and just press OK. So yeah, it will plot this, or I will simply close this, or yeah, you can see again. I simply need to run. I will get all the values, and here I can simply split it and press V vertical and see if I want to display something for my results in my report or something, or I can simply press M. M is for marker, and I can see the values and all those things. So this is how you do the DC, AC analysis and power consumption. And in the coming tutorials, I will be also using this test case to show how to do the PVT for for these parameters. Why it's important to define expressions like this if you want to do the PVT variations also. Okay. Thank you all, and in the next tutorial I will try to show you the stability, and then we'll go to noise and step by step PSRR, CMRR, and maybe TSD also, and also Monte Carlo and PVT.